What if everything you thought you knew about the universe was just the tip of the iceberg? Picture this: a time when the cosmos was a swirling, chaotic soup of energy, long before stars, galaxies, or even light itself existed. Sounds like science fiction, right? But here's the kicker: it's not. This is the story of the early universe, a place filled with mysteries so profound they challenge everything we think we understand about reality. Welcome to a journey through the 30 mysteries of the early universe, where we'll dive into the biggest questions that keep scientists up at night. From the mind-bending singularity of the Big Bang to the invisible forces of dark matter and dark energy, we're about to explore the cosmic puzzles that shape the universe as we know it. But this isn't just a history lesson. By the end of this video, you'll walk away with a deeper understanding of how the universe began, why it looks the way it does, and what secrets it's still hiding. So, whether you're a space enthusiast or just someone who loves a good mystery, stick around because the story of the early universe is stranger, wilder, and more awe-inspiring than anything you've ever imagined. Let's get started. Now, let's dive into the very first mystery that sets the stage for everything else, the Big Bang Singularity. Imagine a moment when the entire universe was compressed into an infinitely small, infinitely dense point. No space, no time, just pure energy. This is the Big Bang Singularity, the starting point of our universe. But here's the thing: our current laws of physics break down when we try to describe it. Why is this so puzzling? Well, according to Einstein's theory of general relativity, the singularity is where gravity becomes infinite, and the equations we use to understand the universe simply stop working. It's like trying to divide by zero. It doesn't make sense. This raises some huge questions. What triggered the Big Bang? What existed before it? And how did everything we see today come from such a tiny, incomprehensible point? Scientists have been grappling with these questions for decades, and one of the leading theories is quantum gravity. Unlike general relativity, which deals with the very large, quantum mechanics deals with the very small. Quantum gravity attempts to bridge these two worlds, suggesting that at the tiniest scales, space and time might behave in ways we can't yet fully understand. Some theories propose that the singularity wasn't a single point but a quantum fluctuation, a tiny ripple in the fabric of reality that set off the birth of the universe. But here's the catch: we don't have the tools yet to test these ideas directly. The conditions of the Big Bang Singularity are so extreme that they're beyond the reach of our current technology. That's why scientists are working on experiments like particle accelerators and space telescopes to gather clues about the early universe. They're also developing new mathematical models to try and piece together what might have happened in those first moments. So, while the Big Bang Singularity remains one of the greatest mysteries of the cosmos, it's also one of the most exciting. It challenges us to rethink our understanding of reality and pushes the boundaries of science itself. And as we move forward, who knows what groundbreaking discoveries might be waiting just around the corner. Next up, we'll explore another mind-bending mystery: cosmic inflation, the rapid expansion of the universe that followed the Big Bang. What caused it and why does it matter? Let's find out. Now, let's shift our focus to another fascinating puzzle of the early universe: cosmic inflation. Picture this: just a fraction of a second after the Big Bang, the universe didn't just expand, it exploded outward at an unimaginable speed. This rapid expansion, known as cosmic inflation, is thought to have lasted for less than a trillionth of a second, yet it set the stage for the universe we see today. But why is this such a big deal, and what makes it such a profound mystery? To understand cosmic inflation, let's start with the evidence. One of the strongest clues comes from the cosmic microwave background, or CMB, which is essentially the afterglow of the Big Bang. The CMB shows an incredibly uniform temperature across the entire universe, almost as if everything was once in close contact. But here's the catch: regions of the universe that are now billions of light years apart couldn't have exchanged heat or information in the time since the Big Bang unless something like inflation happened. Cosmic inflation explains this uniformity by suggesting that the universe expanded so quickly that these regions were once much closer together, allowing them to reach the same temperature before being stretched apart. But that's not all. Inflation also helps explain why the universe appears so flat on large scales. Without inflation, the universe's curvature would be much more pronounced, but the rapid expansion smoothed out any wrinkles, leaving us with the nearly flat geometry we observe today. And then there's the distribution of galaxies and galaxy clusters. Cosmic inflation provides a framework for how tiny quantum fluctuations in the early universe grew into the large-scale structures we see now. So, what's the mystery? Well, while inflation explains a lot, it also raises some big questions. For starters, what caused it? What force or mechanism could have driven the universe to expand so rapidly? Some theories point to a hypothetical field called the inflaton field, which might have provided the energy needed for this explosive growth, but we don't know what this field is made of or how it works. And then there's the question of how inflation ended. If it started, why did it stop, and what happened in that split second when it transitioned into the slower expansion we see today? These unanswered questions make cosmic inflation one of the most intriguing mysteries in cosmology. It's a theory that beautifully explains many of the features of our universe, yet it leaves us with tantalizing gaps in our understanding. Scientists are actively searching for clues, from studying the CMB in greater detail to exploring the nature of dark energy, which might hold some connection to inflation. As we continue to unravel the secrets of the early universe, cosmic inflation reminds us just how much we still have to learn. And with every new discovery, we get a little closer to understanding the forces that shaped everything around us. Up next, we'll explore another cosmic enigma, dark matter, the invisible substance that makes up most of the universe's mass. What is it and why can't we see it? Let's dive in. Now, let's turn our attention to one of the most elusive and puzzling components of the universe, dark matter. Imagine looking up at the night sky and realizing that everything you see, stars, galaxies, and even the vast cosmic web, is just a tiny fraction of what's actually out there. In fact, dark matter makes up about 85% of all the matter in the universe. But here's the catch: we can't see it, touch it, or detect it directly. So, what exactly is dark matter, and why is it so important to understand dark matter? Let's start with what we do know. We first became aware of its existence because of the way galaxies behave. When astronomers observed how stars and galaxies move, they noticed something strange. The visible matter, stars, gas, and dust, wasn't enough to account for the gravitational forces at play. Galaxies were spinning faster than they should, and clusters of galaxies were holding together in ways that defied the laws of physics as we understood them. The only explanation: there had to be some invisible form of matter exerting a gravitational pull, holding everything together. That's dark matter, but what is it made of? That's where things get really interesting. Scientists have proposed several theories, but none have been proven yet. One leading idea is that dark matter consists of particles that don't interact with light or ordinary matter except through gravity. These hypothetical particles, known as WIMP, weakly interacting massive particles, could be everywhere around us, passing through us without us even noticing. Another theory suggests that dark matter might be made up of primordial black holes, tiny black holes formed in the early universe. But so far, we haven't found definitive evidence for either. The search for dark matter is one of the most exciting areas of modern physics. Scientists are using a variety of methods to try and detect it. Deep underground, in labs shielded from cosmic rays, detectors are waiting for the rare moment a dark matter particle might interact with ordinary matter. In space, telescopes are scanning the skies for indirect evidence, like the way dark matter bends light from distant galaxies. a phenomenon known as gravitational lensing. And at particle colliders like the Large Hadron Collider, researchers are smashing particles together at incredible speeds, hoping to create dark matter in the lab. Despite all these efforts, dark matter remains undetected, but its presence is undeniable. Without it, galaxies wouldn't hold together, and the universe as we know it wouldn't exist. It's a reminder of how much we still have to learn about the cosmos. And while dark matter might be invisible, its impact on the universe is anything but. As we continue to explore this cosmic mystery, we're not just searching for answers about dark matter, we're uncovering clues about the very fabric of the universe itself. Up next, we'll dive into another profound enigma: dark energy, the mysterious force driving the accelerated expansion of the universe. What is it, and how does it shape the fate of the cosmos? Let's find out. Now, let's shift our focus to another cosmic puzzle that's just as mysterious as dark matter, if not more so: dark energy. While dark matter holds galaxies together, dark energy is doing something entirely different. It's pushing the universe apart. In fact, dark energy is the force behind the accelerated expansion of the universe, a discovery that completely reshaped our understanding of cosmology. The story of dark energy begins in the late 1990s, when astronomers were studying distant supernova to measure how fast the universe was expanding. They expected to find that the expansion was slowing down over time due to the gravitational pull of all the matter in the universe, but what they found was the opposite. The universe wasn't just expanding, it was expanding faster and faster. This shocking revelation led to the conclusion that some unknown force, later dubbed dark energy, was counteracting gravity and driving this acceleration. So, what exactly is dark energy? That's the million-dollar question. One leading theory suggests that dark energy is a property of space itself, often referred to as the cosmological constant. This idea, first proposed by Albert Einstein, suggests that empty space isn't truly empty. It has an inherent energy that causes it to expand. Another possibility is that dark energy is a dynamic field, something that changes over time and could even evolve in ways we don't yet understand. But despite decades of research, we still don't know which of these theories, if any, is correct. The implications of dark energy are profound. If the universe continues to expand at an accelerating rate, it could lead to a future where galaxies are so far apart that they become invisible to each other. Stars and planets would be isolated, and the universe would grow colder and darker over time, a scenario cosmologists call the Big Freeze. On the other hand, if dark energy behaves differently than we think, it could lead to other outcomes like the Big Rip, where the expansion becomes so extreme that it tears apart galaxies, stars, and even atoms. Dark energy is one of the biggest unsolved problems in cosmology because it challenges our fundamental understanding of physics. It makes up about 68% of the universe's total energy, yet we know almost nothing about it. Scientists are using a variety of tools to study dark energy, from telescopes that map the large-scale structure of the universe to experiments that probe the nature of space and time. But so far, dark energy remains as elusive as ever. As we continue to explore this cosmic mystery, we're not just trying to understand dark energy, we're trying to understand the ultimate fate of the universe itself. And with every discovery, we're reminded of how much we still have to learn about the cosmos. Up next, we'll tackle another intriguing mystery, the horizon problem, which questions why distant regions of the universe have the same temperature despite being too far apart to have interacted. What's the explanation behind this cosmic coincidence? Let's find out. Now, let's turn our attention to a mystery that seems almost too perfect to be true, the horizon problem. Imagine looking at two distant regions of the universe, so far apart that light from one could never have reached the other. Yet when we measure their temperatures, they're nearly identical. How is this possible? This is the essence of the horizon problem, and it's one of the most puzzling questions in cosmology. To understand why this is so strange, let's break it down. In the early universe, light and heat could only travel so far in the time available. This means that regions separated by vast distances shouldn't have had the chance to exchange energy or reach the same temperature. It's like having 2 cups of coffee in different cities cooling down to the exact same temperature without ever being in contact. So why does the universe appear so uniform? This is where cosmic inflation comes in. Proposed in the early 1980s, inflation is the idea that the universe underwent an incredibly rapid expansion just moments after the Big Bang. In a fraction of a second, the universe expanded faster than the speed of light, stretching out tiny regions that were once in close contact. This rapid expansion would have smoothed out any temperature differences, creating the uniform cosmic microwave background we observe today. Think of it like blowing up a balloon. If you draw 2 dots close together on a deflated balloon and then inflate it, those dots will move far apart. Inflation works similarly, but on a cosmic scale. It explains how regions that were once close enough to interact could now be separated by vast distances, yet still share the same temperature. But inflation isn't just a neat solution to the horizon problem. It also ties into other mysteries we've explored, like the flatness problem and the formation of the cosmic web. It's a cornerstone of modern cosmology, providing a framework for understanding the large-scale structure of the universe. Still, inflation isn't without its challenges. For one, we don't yet know what caused this rapid expansion or how it stopped. And while the theory makes predictions that align with observations, it's difficult to test directly. The horizon problem reminds us that the universe is full of surprises, and sometimes the answers lie in the most unexpected places. As we continue to probe the early universe, we're not just solving puzzles, we're uncovering the story of how everything came to be. Next, we'll explore another cosmic mystery, the flatness problem, which asks why the universe appears so perfectly balanced on the edge of geometry. What does this mean for the fate of the cosmos? Let's dive in. Now, let's shift our focus to another fascinating puzzle in the cosmos, the flatness problem. Picture the universe as a vast, 3-dimensional canvas. If you were to measure its geometry, you'd expect it to curve in some way, either inward like a sphere or outward like a saddle. But here's the twist. Observations show that the universe is almost perfectly flat. This might sound like a minor detail, but it's actually a profound mystery with huge implications for the fate of the cosmos. To understand why this is so puzzling, let's take a step back. The shape of the universe is tied to its density. If the universe had too much matter and energy, it would curve inward, eventually collapsing in on itself in what's called a big crunch. If it had too little, it would curve outward, expanding forever into a cold, empty void. But instead, the universe seems to be balanced on a knife's edge, with just the right amount of density to keep it flat. The odds of this happening by chance are astronomically low, like balancing a pencil on its tip for billions of years. So, how did the universe achieve this perfect balance? This is where cosmic inflation steps in once again. Remember that rapid expansion we talked about earlier? Inflation doesn't just solve the horizon problem, it also explains why the universe appears so flat. Imagine taking a tiny, curved piece of space and stretching it out to an enormous size. The more you stretch it, the flatter it becomes, just like how a small section of a balloon looks flat when you blow it up. Inflation did this on a cosmic scale, smoothing out any curvature and leaving the universe with the flat geometry we observe today. But the flatness problem isn't just about geometry, it's also about the universe's destiny. A flat universe suggests that the total density of matter and energy is precisely balanced, meaning the cosmos will continue expanding forever, though at an ever-slowing rate. This ties directly into the mysteries of dark energy, which we'll explore later, and raises questions about the ultimate fate of everything we see. The flatness problem reminds us that the universe is a finely tuned system, full of delicate balances and hidden connections. It's a reminder that even the simplest observations, like the shape of space itself, can lead to some of the deepest questions in science. Next, we'll uncover another cosmic enigma, the mystery of the missing baryons, the ordinary matter that seems to have vanished from the universe. Where could it be hiding? Let's find out. Now, let's turn our attention to a mystery that's closer to home literally. We're talking about the missing baryons, the ordinary matter that makes up everything we can see, from stars and planets to you and me. But here's the catch. When scientists tally up all the baryons in the universe, a significant chunk seems to be missing. So, where did they go? This is the puzzle of the missing baryons, and it's one of the most intriguing mysteries in modern cosmology. To put it simply, baryons are the building blocks of the visible universe. They include protons and neutrons, the particles that form atoms, which in turn make up everything from galaxies to galaxies. Based on our understanding of the Big Bang and the early universe, we can predict how much baryonic matter should exist today. But when astronomers look around, they find that about 30 to 40% of these baryons are unaccounted for. It's like doing a cosmic inventory and realizing half your stuff has vanished without a trace. So, where could these missing baryons be hiding? One leading theory suggests they're lurking in the vast, diffuse regions of space known as the warm-hot intergalactic medium, or WIM for short. This is the space between galaxies, filled with incredibly thin gas that's so hot it glows faintly in X-rays. Detecting this gas is no easy task. It's like trying to spot a single candle in a foggy field from miles away. But thanks to advanced telescopes and innovative techniques, scientists are beginning to piece together this cosmic puzzle. Another possibility is that the missing baryons are tied up in cosmic filaments, the thread-like structures that form the cosmic web. These filaments, made of dark matter and gas, stretch across the universe, connecting galaxies like a vast, invisible network. The baryons in these filaments are so spread out and faint that they're incredibly difficult to detect. But by studying the way light from distant quasars passes through these regions, astronomers are slowly mapping out where these elusive baryons might be hiding. The search for missing baryons isn't just about solving a cosmic accounting problem, it's about understanding the full story of how the universe evolved. These baryons are the raw material for stars, galaxies, and ultimately life itself. By finding them, we can fill in crucial gaps in our knowledge of the cosmos and get a clearer picture of how everything came to be. As we continue to explore this mystery, one thing is clear: the universe still has plenty of secrets to reveal. Next, we'll dive into another cosmic enigma, the first stars, the ancient beacons that lit up the early universe and set the stage for everything that followed. How did they form, and why are they so elusive? Let's find out. Now, let's journey back to a time when the universe was still in its infancy, a time before galaxies, before planets, and even before the stars we see today. We're talking about the very first stars, known as population 3 stars. These ancient celestial giants were the pioneers of light in a dark, young universe, and their story is one of the most fascinating mysteries in cosmology. Population 3 stars were unlike anything we see in the modern universe. They were massive, hundreds of times heavier than our Sun, and composed almost entirely of hydrogen and helium, the only elements that existed in the early universe. These stars didn't have the heavier elements like carbon, oxygen, or iron that are essential for the stars and planets we know today. But despite their simplicity, they played a crucial role in shaping the cosmos as we know it. So how did these first stars form? In the early universe after the Big Bang, the cosmos was a hot, dense soup of particles. As the universe expanded and cooled, gravity began to pull together clumps of hydrogen and helium gas. These clumps grew denser and hotter until, eventually, nuclear fusion ignited in their cores, and the first stars were born. This process marked the end of the cosmic dark ages and the beginning of the era of light. But here's the catch: we've never actually seen a population 3 star. They're incredibly elusive, and for good reason. These stars lived fast and died young, burning through their fuel in just a few million years before exploding as supernova. Their light, which traveled across the universe for billions of years, is now so faint that it's nearly impossible to detect with our current telescopes. It's like trying to spot a single firefly in a pitch-black forest from thousands of miles away. Despite their elusiveness, the impact of population 3 stars is undeniable. When they exploded, they seeded the universe with the first heavy elements like carbon, oxygen, and iron. These elements became the building blocks for future generations of stars, planets, and even life itself. Without these ancient stars, the universe as we know it simply wouldn't exist. Scientists are now using some of the most advanced telescopes ever built to search for clues about these first stars. By studying the faintest, most distant galaxies, they hope to catch a glimpse of the light from population 3 stars or the remnants they left behind. It's a cosmic detective story, and every new discovery brings us closer to understanding how the universe lit up for the first time. As we continue to unravel the mystery of the first stars, we're reminded of just how much the universe has changed since its fiery beginnings. Next, we'll explore another pivotal moment in cosmic history, the reionization era, when the universe transformed from a dark, neutral state to one filled with ionized gas. What caused this dramatic shift, and why is it still such a mystery? Let's find out. Now, let's step into a transformative chapter of cosmic history, the reionization era. This pivotal period marked the universe's transition from a dark, neutral state to one filled with ionized gas, a process that fundamentally changed the fabric of the cosmos. But what exactly triggered this dramatic shift, and why does it remain one of the most perplexing mysteries of the early universe? After the first stars, known as population 3 stars, ignited and began to shine, they didn't just light up the universe, they also began to alter its very structure. These massive stars emitted intense ultraviolet radiation, which had the power to strip electrons from hydrogen atoms, a process known as ionization. This radiation began to carve out bubbles of ionized gas around the stars, slowly but surely changing the universe from a neutral state to one filled with charged particles. Over hundreds of millions of years, these bubbles grew and merged, eventually filling the cosmos with ionized gas and bringing an end to the cosmic dark ages. But here's where things get tricky. While we know that the first stars played a key role in reionization, the process wasn't as straightforward as it might seem. For one, the radiation from these early stars alone doesn't fully explain how the entire universe became ionized. Scientists believe that other sources of energy, such as quasars, bright, energetic objects powered by supermassive black holes, may have also contributed to this cosmic transformation. Yet, the exact balance between these different sources of radiation remains unclear, leaving a gap in our understanding of how reionization unfolded. Another layer of mystery lies in the timing of this process. Observations of distant galaxies and the cosmic microwave background suggest that reionization began around 200 million years after the Big Bang and lasted for several hundred million years. But pinning down the exact timeline has proven to be a challenge. Some regions of the universe may have reionized earlier than others, creating a patchwork of ionized and neutral gas that complicates our picture of this era. This uneven progression raises questions about how the first stars and galaxies formed and interacted during this critical period. Adding to the intrigue is the fact that reionization didn't just change the state of the universe, it also had lasting effects on the formation of galaxies. The ionized gas created by this process influenced how matter clumped together, shaping the growth of galaxies and the large-scale structure of the cosmos. Yet, the details of how this interplay unfolded are still shrouded in uncertainty. making reionization a key area of research for cosmologists. Today, scientists are using cutting-edge telescopes to peer back in time and study this enigmatic era. By observing the faint light from the most distant galaxies and quasars, they hope to uncover clues about how reionization occurred and what drove it. Each new discovery brings us closer to understanding this cosmic turning point, but many questions remain unanswered. As we continue to explore the reionization era, we're reminded of just how dynamic and complex the early universe was. Next, we'll turn our attention to another cosmic mystery, the Great Cosmic Web, the vast network of dark matter and gas that forms the backbone of the universe. How did this intricate structure come to be, and what secrets does it hold about the origins of the cosmos? Let's dive in. Now, let's shift our gaze to one of the most awe-inspiring structures in the cosmos, the Great Cosmic Web. Imagine the universe not as a random scattering of galaxies, but as an intricate network, a vast tapestry woven together by invisible threads of dark matter and gravity. This cosmic web is the backbone of the universe, connecting galaxies and galaxy clusters in a sprawling, filamentary structure that stretches across billions of light years. But how did this colossal network come to be, and why does its formation remain one of the most fascinating mysteries of the early universe? To understand the cosmic web, we need to start with dark matter, the unseen force that makes up about 85% of the universe's total matter. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is felt through its gravitational pull, which shapes the distribution of galaxies and the large-scale structure of the universe. In the early universe, tiny fluctuations in the density of dark matter created a framework, a kind of cosmic blueprint, that would later guide the formation of galaxies and galaxy clusters. Over billions of years, gravity amplified these fluctuations, pulling matter into dense regions and leaving vast, empty voids in between. The result: a web-like structure of filaments and nodes where galaxies cluster together like beads on a string. But here's the twist: while we have a good grasp of how dark matter laid the groundwork for the cosmic web, the exact process of its formation is still shrouded in mystery. For instance, how did the first filaments of dark matter form, and what determined their thickness and distribution? Scientists believe that quantum fluctuations in the early universe played a role, but the details of how these tiny ripples grew into the massive structures we see today are still being unraveled. Adding to the complexity is the role of ordinary matter, the gas and dust that eventually formed stars and galaxies. As this matter flowed along the dark matter filaments, it created the glowing strands of the cosmic web we observe today. Yet, the interplay between dark matter and ordinary matter is far from fully understood, leaving gaps in our knowledge of how the web evolved. Another layer of intrigue lies in the voids, the vast, empty regions that make up most of the cosmic web. These voids are not entirely empty. They contain sparse amounts of gas and dark matter, but their sheer size and emptiness raise questions about how they formed and what role they play in the universe's structure. Some theories suggest that voids are the result of matter being pulled away by gravity, leaving behind these cosmic deserts. Others propose that they may have formed due to the expansion of the universe itself. Whatever the case, voids are a crucial part of the cosmic web, and understanding their origins could shed light on the web's overall structure. Today, astronomers are using powerful telescopes and sophisticated simulations to map the cosmic web in unprecedented detail. By studying the distribution of galaxies and the light from distant quasars, they're piecing together a clearer picture of this vast network, yet many questions remain. For example, how did the first filaments of the cosmic web form? And what role did dark energy play in shaping its evolution? And how do the properties of the cosmic web influence the formation and behavior of galaxies? Each discovery brings us closer to answering these questions, but the cosmic web continues to be a source of wonder and mystery. As we marvel at the grandeur of the cosmic web, we're reminded of the intricate and interconnected nature of the universe. Next, we'll explore another enigmatic piece of the cosmic puzzle: primordial black holes, hypothetical objects that may have formed in the early universe and could hold clues to some of its deepest mysteries. What are they, and how might they reshape our understanding of the cosmos? Let's find out. Now, let's turn our attention to one of the most intriguing possibilities in the early universe: primordial black holes. Unlike the black holes we're familiar with, which form from the collapse of massive stars, primordial black holes are thought to have emerged in the first moments after the Big Bang. These hypothetical objects could be as small as an atom or as massive as a star, and their existence might hold the key to solving some of the universe's biggest mysteries. So, how could black holes form so early in the universe's history? The answer lies in the extreme conditions that existed just after the Big Bang. During this time, the universe was incredibly dense and hot, with tiny fluctuations in density scattered throughout. In some regions, these fluctuations could have been so intense that they caused matter to collapse directly into black holes, bypassing the need for stars altogether. These primordial black holes would have been born in the chaos of the early universe, and some of them might still exist today, lurking in the darkness of space. But why are scientists so interested in these ancient black holes? One reason is their potential connection to dark matter. As we've discussed earlier, dark matter makes up a significant portion of the universe's mass, but we still don't know what it's made of. Primordial black holes could be a candidate. If they exist in large enough numbers, they might account for some or even all of the dark matter we observe. This idea has sparked a lot of excitement, but it's also highly speculative. Detecting these elusive objects is no easy task, and so far we have no direct evidence that they exist. One of the biggest challenges in searching for primordial black holes is their size. If they're very small, they could be almost impossible to detect directly. However, scientists have come up with clever ways to look for them. For example, if a primordial black hole passes between us and a distant star, its gravity could bend the star's light, causing a brief brightening known as microlensing. By monitoring millions of stars, astronomers hope to catch these rare events and gather clues about the presence of primordial black holes. Another approach involves looking for the effects of these black holes on the cosmic microwave background, the faint afterglow of the Big Bang. If primordial black holes were abundant in the early universe, they might have left subtle imprints in this ancient light. Despite these efforts, the search for primordial black holes remains a daunting challenge. Their hypothetical nature means we're dealing with a lot of unknowns, and even if they do exist, they might be incredibly rare or difficult to distinguish from other cosmic phenomena. Yet the possibility of discovering them is tantalizing. If primordial black holes are real, they could revolutionize our understanding of the early universe, dark matter, and even the nature of black holes themselves. As we ponder the mysteries of primordial black holes, we're reminded of how much we still have to learn about the cosmos. These ancient objects, if they exist, could be hiding in plain sight, waiting to reveal secrets about the universe's infancy. Next, we'll explore another profound mystery, the matter-antimatter asymmetry, which asks why the universe is dominated by matter instead of antimatter. What caused this imbalance, and what does it mean for our existence? Let's dive in. Now, let's shift our focus to one of the most fundamental questions in cosmology. Why does the universe have so much matter and so little antimatter? This mystery, known as the matter-antimatter asymmetry, is one of the biggest puzzles in science. According to our current understanding, the Big Bang should have created equal amounts of matter and antimatter. But if that were the case, they would have annihilated each other, leaving behind a universe filled with nothing but energy. Yet here we are, in a universe dominated by matter, with stars, planets, and galaxies all around us. So, what happened to all the antimatter? To understand this imbalance, we need to take a closer look at the early universe. In the first moments after the Big Bang, particles and antiparticles were constantly being created and destroyed. But for some reason, matter ended up slightly outnumbering antimatter. This tiny difference, just one extra matter particle for every billion matter-antimatter pairs, was enough to tip the scales. After the rest annihilated, the leftover matter became the building blocks of everything we see today. But why did this imbalance occur in the first place? One of the leading theories to explain this mystery is something called CP violation. CP stands for charge parity, and it's a symmetry that describes how particles behave under certain transformations. In simple terms, CP symmetry means that the laws of physics should work the same way for particles and their mirror image antiparticles. But experiments have shown that this symmetry isn't perfect. There are small differences in how matter and antimatter behave. These differences, known as CP violation, might explain why matter ended up dominating the universe. The first evidence of CP violation was discovered in the 1960s in the behavior of particles called kaons. Since then, similar effects have been observed in other particles like B mesons. While these discoveries are exciting, they still don't fully account for the matter-antimatter imbalance we see today. The amount of CP violation observed so far is far too small to explain why the universe is filled with matter. This has led scientists to search for other sources of CP violation, possibly involving particles we haven't discovered yet. Another intriguing possibility is that the imbalance might be linked to the conditions of the early universe. For example, some theories suggest that the universe underwent a phase transition shortly after the Big Bang, similar to water freezing into ice. This transition could have created tiny bubbles where matter and antimatter were unevenly distributed, leading to the dominance of matter we see today. Other ideas involve exotic particles or forces that existed only in the early universe and played a role in tipping the balance. The matter-antimatter asymmetry isn't just a scientific curiosity, it's crucial for our existence. Without this imbalance, the universe would be empty, with no stars, no planets, and no life. Understanding how and why this asymmetry occurred could reveal fundamental truths about the nature of reality. It could also help us answer other big questions, like what happened in the first moments after the Big Bang and why the universe looks the way it does. As we continue to explore this mystery, we're reminded of how delicate and finely tuned the universe seems to be. The fact that we exist at all is a testament to the tiny, yet profound, differences that shape the cosmos. Next, we'll turn our attention to another cosmic puzzle: the anomalies in the cosmic microwave background, the oldest light in the universe. What do these strange patterns tell us about the early universe, and could they challenge our understanding of cosmology? Let's find out. Now, let's dive into another fascinating mystery of the early universe: the anomalies in the cosmic microwave background, or CMB. This ancient light, often called the afterglow of the Big Bang, holds clues about the universe's infancy. But not everything in the CMB fits neatly into our current understanding. Some features, like the cold spot and other unexpected patterns, have left scientists scratching their heads. What do these anomalies mean, and could they challenge our fundamental ideas about the cosmos? The cosmic microwave background is essentially a snapshot of the universe when it was just 380,000 years old. At that time, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. This light has been stretched over billions of years into the microwave radiation we detect today. The CMB is remarkably uniform, but it's not perfectly smooth. Tiny fluctuations in temperature and density reveal the seeds of galaxies and galaxy clusters we see now. However, some of these fluctuations are far more puzzling than others. One of the most famous anomalies is the cold spot, a region in the CMB that's significantly cooler than its surroundings. At first glance, it might seem like a minor detail, but its size and temperature difference make it stand out. Some theories suggest the cold spot could be a sign of a cosmic defect, like a texture in space-time left over from the early universe. Others propose it might be evidence of a collision with another universe, a mind-bending idea tied to the multiverse theory. While these explanations are speculative, they highlight how much we still have to learn about the universe's origins. Another intriguing anomaly is the unexpected alignment of certain features in the CMB, sometimes referred to as the axis of evil. This term might sound dramatic, but it reflects how these patterns seem to defy the standard model of cosmology. According to our current understanding, the universe should be isotropic, meaning it looks the same in all directions. Yet, the CMB shows hints of a preferred direction, challenging this assumption. Could this be a sign of new physics, or is it simply a statistical fluke? Scientists are still debating. These anomalies aren't just curiosities, they could have profound implications for our understanding of the early universe. If they're real and not just random quirks, they might point to phenomena we haven't yet discovered. For example, they could hint at exotic particles, unknown forces, or even modifications to Einstein's theory of gravity. Alternatively, they might reveal that our current models of the universe's evolution are incomplete or need refinement. The search for answers continues, with new missions and telescopes designed to study the CMB in greater detail. Each discovery brings us closer to understanding these anomalies and what they mean for the cosmos. As we unravel these mysteries, we're reminded that the universe is full of surprises, and even the oldest light in the sky still has secrets to reveal. Next, we'll explore another cosmic puzzle, the Hubble tension, a discrepancy in measurements of the universe's expansion rate. What does this tension tell us about the fate of the cosmos? Let's find out. Now, let's turn our attention to another cosmic conundrum that has scientists buzzing: the Hubble tension. This mystery revolves around a puzzling discrepancy in how fast the universe is expanding. You might think measuring something as fundamental as the universe's expansion rate would be straightforward, but it turns out it's anything but. In fact, this tension has sparked one of the most heated debates in modern cosmology, and it could reshape our understanding of the cosmos. The Hubble tension arises from two primary methods used to measure the universe's expansion rate, often referred to as the Hubble constant. The first method looks at the cosmic microwave background, the ancient light we just discussed, which provides a snapshot of the early universe. By analyzing the CMB, scientists can calculate how fast the universe was expanding shortly after the Big Bang and extrapolate that rate to the present day. The second method involves observing nearby objects like supernova and Cepheid variable stars, which act as cosmic yardsticks. By measuring their distances and how fast they're moving away from us, astronomers can directly estimate the current expansion rate. Here's where things get interesting. These two methods, which should ideally agree, are giving us different answers. The CMB-based measurements suggest a slower expansion rate, while observations of nearby objects point to a faster one. This discrepancy isn't just a small margin of error. It's significant enough to suggest that something fundamental might be missing from our current understanding of the universe. So, what could be causing this tension? One possibility is that there's an unknown ingredient in the cosmic recipe. For instance, some scientists speculate that there might be an additional type of neutrino or a new form of dark energy at play. Others suggest that our understanding of dark matter might need an update. There's even the tantalizing idea that the laws of physics themselves could behave differently on cosmic scales than they do in our local neighborhood. The implications of the Hubble tension are profound. If it's real and not just a measurement error, it could mean that our standard model of cosmology, which has been remarkably successful so far, is incomplete. This model, known as lambda cold dark matter or lambda CDM, describes a universe dominated by dark energy and dark matter, but the Hubble tension might be hinting that we need to tweak or even overhaul this framework. The debate among scientists is far from settled. Some argue that the tension could be resolved with better measurements or by refining existing techniques. Others believe it's a sign of new physics waiting to be discovered. To tackle this mystery, astronomers are using cutting-edge tools like the James Webb Space Telescope and upcoming missions designed to measure the Hubble constant with unprecedented precision. As we continue to explore this cosmic puzzle, one thing is clear. The Hubble tension is more than just a scientific disagreement. It's a window into the unknown. Whether it leads us to new particles, revised laws of physics, or a deeper understanding of dark energy, it reminds us that the universe still has plenty of surprises in store. Next, we'll journey into the epoch of galaxy formation, where we'll uncover how the first galaxies emerged from the cosmic darkness and shaped the universe as we know it today. Now, let's shift our gaze to a time when the universe was still in its infancy, the epoch of galaxy formation. This period marks one of the most transformative phases in cosmic history, when the first galaxies began to take shape, lighting up the darkness of the early universe. But how did these colossal structures emerge from the primordial soup of gas and dark matter, and what can they tell us about the universe's earliest days? The formation of the first galaxies is a mystery that takes us back to a time just a few 100 million years after the Big Bang. During this era, the universe was a vastly different place, dense, hot, and filled with swirling clouds of hydrogen and helium. Gravity played the starring role, pulling these clouds together into clumps that eventually collapsed under their own weight, igniting the first stars. These stars, in turn, gathered into groups, forming the earliest galaxies, but the details of how this process unfolded remain elusive. One of the biggest challenges in studying this epoch is the sheer distance and time involved. The light from these ancient galaxies has traveled for billions of years to reach us, stretched and dimmed by the expansion of the universe. Detecting this faint, redshifted light requires some of the most advanced telescopes ever built, like the James Webb Space Telescope. Even with these tools, observing the first galaxies is like trying to spot a candle flickering in a distant fog. Another hurdle is understanding the role of dark matter in galaxy formation. While we can't see dark matter directly, we know it played a crucial part in shaping the universe's large-scale structure. Dark matter acted as a cosmic scaffold, providing the gravitational pull needed to gather gas and stars into galaxies. But how exactly did this invisible material interact with ordinary matter to create the galaxies we see today? This question remains a key area of research. The first galaxies also hold clues about the universe's chemical evolution. These early structures were made up of the simplest elements, hydrogen and helium, with almost no heavier elements like carbon or oxygen. Over time, as stars lived and died, they forged these heavier elements in their cores and scattered them across the cosmos through supernova explosions. This process, known as cosmic recycling, gradually enriched the universe, paving the way for the formation of planets and eventually life. By studying the first galaxies, we can trace the origins of the elements that make up everything around us. But perhaps the most intriguing aspect of this epoch is what it reveals about the universe's capacity for change. The first galaxies were small and faint compared to the majestic spirals and ellipticals we see today. Over billions of years, they grew, merged, and evolved, driven by the relentless pull of gravity and the explosive energy of supermassive black holes. This cosmic dance of creation and destruction continues to shape the universe, and the first galaxies are the starting point of that story. As we peer deeper into the past, we're not just uncovering the history of galaxies, we're uncovering the history of the universe itself. Each ancient galaxy is a time capsule, preserving the conditions of the early cosmos and offering glimpses into the forces that shaped it. And while many questions remain, one thing is certain. The epoch of galaxy formation is a testament to the universe's boundless creativity and complexity. Next, we'll explore the nature of quasars, the brilliant beacons that lit up the early universe and continue to captivate astronomers today. Now, let's turn our attention to one of the most dazzling and enigmatic phenomena in the cosmos: quasars. These incredibly bright objects powered by supermassive black holes are like cosmic lighthouses, shining across unimaginable distances and lighting up the early universe. But what exactly are quasars, and why do they hold such a pivotal place in our understanding of the cosmos? Quasars, short for quasi-stellar radio sources, are among the most luminous objects in the universe. At their heart lies a supermassive black hole, millions to billions of times more massive than our Sun. As matter spirals into these black holes, it heats up to extreme temperatures, releasing vast amounts of energy in the form of light and radiation. This process makes quasars so bright that they can outshine entire galaxies, even from billions of light years away. In the early universe, quasars played a crucial role in shaping their surroundings. They acted as cosmic engines, driving the growth of galaxies and influencing the distribution of matter across vast regions of space. The intense radiation emitted by quasars ionized the surrounding gas, stripping electrons from atoms and creating the conditions for the universe to transition from a dark, neutral state to one filled with light. This era, known as the Epoch of Reionization, was a turning point in cosmic history, and quasars were at the forefront of this transformation. But studying quasars is no easy task. Their immense distance means that the light we observe from them today left when the universe was just a fraction of its current age. This light has been stretched and redshifted by the expansion of the universe, making it challenging to detect and analyze. Even with advanced telescopes like the James Webb Space Telescope, capturing the faint signals from these ancient objects requires cutting-edge technology and meticulous observation. Another challenge lies in understanding the relationship between quasars and their host galaxies. While we know that quasars are powered by supermassive black holes, the exact mechanisms that trigger their incredible brightness remain a mystery. Some theories suggest that galaxy collisions or the rapid accretion of gas might fuel these cosmic powerhouses, but the details are still unclear. Unraveling this connection is key to understanding how galaxies and their central black holes co-evolve over time. Quasars also offer a unique window into the early universe. By studying their light, astronomers can probe the conditions of the cosmos billions of years ago. The spectra of quasars reveal the presence of elements like hydrogen and helium, as well as the distribution of matter along the line of sight. This information helps us piece together the history of the universe from its earliest moments to the present day. Despite their brilliance, quasars are fleeting phenomena. Over time, as the supermassive black holes at their centers consume the surrounding gas, quasars fade and become dormant. This means that the quasars we observe today are relics of a bygone era, offering a glimpse into a time when the universe was young and chaotic. The study of quasars is a testament to the universe's capacity for both creation and destruction. These luminous objects, born from the most extreme conditions, have shaped the cosmos in profound ways. Yet they remain shrouded in mystery, challenging our understanding of the forces that govern the universe. As we continue to explore these cosmic beacons, we're not just uncovering the secrets of quasars, we're uncovering the story of the universe itself. Next, we'll delve into the mystery of the first supermassive black holes and how they formed so quickly after the Big Bang. Now, shifting our gaze to another cosmic enigma, let's explore the mystery of the first supermassive black holes. These colossal giants, millions to billions of times more massive than our Sun, appeared surprisingly early in the universe's history. But how did they grow so massive so quickly? This question has puzzled astronomers for decades, and the answers could reshape our understanding of the cosmos. One leading theory is the direct collapse model. Imagine a massive cloud of gas in the early universe collapsing under its own gravity without ever forming stars. Instead of fragmenting into smaller clumps, this cloud could have collapsed directly into a black hole, creating a supermassive seed in a relatively short time. These seeds, already massive from the start, would then grow even larger by devouring surrounding gas and merging with other black holes. This process could explain how supermassive black holes existed when the universe was less than 1 billion years old. But the direct collapse model isn't without its challenges. For this scenario to work, the gas cloud would need to avoid cooling and fragmenting, which requires specific conditions. Some scientists suggest that intense radiation from nearby galaxies or the first stars could have heated the gas, preventing it from breaking apart. Others propose that the early universe's unique environment, with its high density and rapid expansion, might have provided the perfect conditions for such massive collapses. Another intriguing possibility is that supermassive black holes formed from the remnants of the first stars. These early stars, known as population 3 stars, were incredibly massive and short-lived. When they died, they could have left behind black holes that grew rapidly by merging with others or accreting gas. However, this process would take longer than the direct collapse model, making it harder to explain the presence of supermassive black holes in the very early universe. The formation of these early supermassive black holes has profound implications for galaxy formation. Supermassive black holes are found at the centers of most galaxies, including our own Milky Way. Their growth and activity are closely tied to the evolution of their host galaxies. For example, the energy released by accreting black holes can heat surrounding gas, preventing it from forming stars and regulating the growth of galaxies. This feedback mechanism suggests that supermassive black holes aren't just passive inhabitants of galaxies, they're active participants in shaping their cosmic environments. Understanding how the first supermassive black holes formed also sheds light on the broader history of the universe. These objects are like cosmic time capsules, preserving clues about the conditions of the early universe. By studying them, we can learn about the distribution of matter, the growth of structures, and the interplay between gravity and radiation in the cosmos. Yet, many questions remain. How common were these early supermassive black holes? What role did they play in the reionization of the universe, and how did they influence the formation of the first galaxies? These are just some of the mysteries that astronomers are working to unravel. As we continue to probe the depths of space and time, the story of the first supermassive black holes reminds us of the universe's capacity for both wonder and complexity. These ancient giants, born in the chaos of the early cosmos, continue to challenge our understanding and inspire our curiosity. Next, we'll explore how the universe transitioned from the Dark Ages to the era of light, a period that marked the dawn of the cosmos as we know it. Now, let's journey into one of the most transformative periods in cosmic history, the end of the Dark Ages. This era marks the universe's transition from a cold, dark expanse to a vibrant, illuminated cosmos filled with the first stars and galaxies. But how did this dramatic shift happen, and what role did the first stars and galaxies play in bringing light to the universe? These questions lie at the heart of this cosmic mystery. The Dark Ages began shortly after the Big Bang, when the universe was a dense, hot soup of particles. As it expanded and cooled, protons and electrons combined to form neutral hydrogen, creating a foggy, opaque environment. During this time, no stars or galaxies existed, and the universe was shrouded in darkness. This period lasted for hundreds of millions of years, until something extraordinary happened. The first stars ignited, piercing through the cosmic gloom and heralding the dawn of light. These first stars, known as population 3 stars, were unlike anything we see today. They were massive, hot, and incredibly bright, composed almost entirely of hydrogen and helium. Their intense ultraviolet radiation began to ionize the surrounding hydrogen gas, gradually clearing the fog and allowing light to travel freely through space. This process, known as reionization, marked the end of the Dark Ages and the beginning of the epoch of reionization. But the story doesn't end with the first stars. The formation of the first galaxies played a crucial role in this cosmic transformation. As these early galaxies grew, they pulled in gas and dust, fueling the birth of more stars. The combined light from these stars, along with the radiation from supermassive black holes at the centers of galaxies, continued to ionize the surrounding hydrogen, further illuminating the universe. Over time, this process transformed the cosmos from a dark, neutral state into the vibrant, ionized universe we observe today. Yet many questions remain about this pivotal period. How quickly did reionization occur? What were the properties of the first stars and galaxies? And how did their light interact with the surrounding gas to shape the universe's evolution? Astronomers are using powerful telescopes like the James Webb Space Telescope to peer back in time and study this era in unprecedented detail. By observing the faint light from the earliest galaxies, they hope to uncover the secrets of the cosmic dawn. The end of the Dark Ages wasn't just a turning point for the universe, it was the foundation for everything that followed. The first stars and galaxies laid the groundwork for the complex structures we see today, from galaxies and clusters to the cosmic web itself. Understanding this transition helps us piece together the story of how the universe evolved from a simple, dark beginning to the rich, diverse cosmos we inhabit. As we continue to explore this cosmic dawn, we're reminded of the universe's remarkable capacity for change. From darkness to light, from simplicity to complexity, the end of the Dark Ages was a pivotal chapter in the grand narrative of the cosmos. Next, we'll delve into the ultimate question: what lies ahead for the universe, and how will its story unfold in the distant future? Now, let's turn our gaze toward the future, a future so vast and uncertain that it challenges our very understanding of existence. What lies ahead for the universe? This question leads us to one of the most profound mysteries of all, the ultimate fate of the cosmos. Will it expand forever, collapse back on itself, or tear apart in a dramatic finale? The answers to these questions are as fascinating as they are speculative, and they hinge on the delicate balance of forces shaping the universe. One of the leading theories about the universe's fate is the Big Freeze, also known as the heat death scenario. In this scenario, the universe continues to expand at an accelerating rate driven by dark energy. Over trillions of years, galaxies will drift farther apart, stars will burn out, and the cosmos will grow colder and darker. Eventually, all that will remain is a vast, empty expanse with temperatures approaching absolute zero. It's a chilling thought, a universe where all activity ceases and time itself becomes meaningless. But the Big Freeze isn't the only possibility. Another intriguing scenario is the Big Crunch, a dramatic reversal of the universe's expansion. In this model, the gravitational pull of all the matter in the cosmos eventually overcomes the force of dark energy, causing the universe to collapse back in on itself. Galaxies, stars, and even atoms will be crushed together in a fiery, chaotic end. Some scientists speculate that this collapse could trigger another Big Bang, leading to a cyclical universe that expands and contracts endlessly. It's a cosmic dance of creation and destruction, repeating itself over and over. Then there's the Big Rip, a scenario as dramatic as it sounds. If dark energy grows stronger over time, it could eventually overpower all other forces, tearing apart galaxies, stars, planets, and even atoms themselves. The universe would end not with a whimper, but with a violent, unstoppable force ripping everything apart. This scenario paints a picture of a universe that doesn't just fade away, it shatters into nothingness. Each of these scenarios, the Big Freeze, the Big Crunch, and the Big Rip, offers a glimpse into the possible futures of the cosmos. But which one will come to pass? The answer depends on the nature of dark energy, the amount of matter in the universe, and the precise balance of forces at play. These are questions that scientists are still working to answer, using observations of distant supernova, the cosmic microwave background, and the large-scale structure of the universe. As we ponder the fate of the universe, we're reminded of the delicate and dynamic nature of existence. The cosmos is not static. It's a living, evolving entity shaped by forces we're only beginning to understand. Whether it ends in a cold, silent expanse, a fiery collapse, or a dramatic tear, the universe's fate is a testament to the incredible complexity and mystery of the cosmos. Next, we'll explore another mind-bending idea. Could our universe be just one of many in a vast multiverse? Now, let's shift our perspective from the fate of our universe to an even grander idea, one that stretches the boundaries of imagination. What if our universe isn't the only one? What if there are countless other universes, each with its own set of physical laws and realities? This is the essence of the multiverse theory, a concept that has sparked both fascination and fierce debate among scientists and philosophers alike. The multiverse theory suggests that our universe might be just one of many, existing alongside others in a vast, interconnected cosmic landscape. This idea isn't just science fiction, it's rooted in some of the most advanced theories in physics, including quantum mechanics and string theory. For example, the concept of eternal inflation proposes that our universe is just one bubble in an endless sea of expanding space, with other bubbles representing entirely separate universes. Each of these universes could have different physical constants, dimensions, and even forms of matter, making them utterly alien to our own. But why is the multiverse theory so controversial? For one, it's incredibly difficult to test, since these other universes, by definition, exist beyond the observable boundaries of our own. We have no direct way to detect or study them. This lack of empirical evidence has led some critics to argue that the multiverse is more philosophy than science. Others, however, see it as a natural extension of our understanding of the cosmos, offering potential explanations for some of the biggest mysteries in physics, like why the constants of nature, such as the speed of light or the strength of gravity, seem so finely tuned to allow life to exist. One of the most intriguing arguments for the multiverse comes from the idea of the anthropic principle. This principle suggests that the conditions in our universe appear just right for life because in a multiverse with countless variations, it's inevitable that at least one universe would have the right parameters. In other words, we find ourselves in a universe that supports life because, well, we couldn't exist in one that doesn't. It's a mind-bending thought, but one that highlights the profound implications of the multiverse theory. Despite its speculative nature, the multiverse has captured the imagination of scientists and the public alike. It challenges us to think beyond the limits of our observable universe and consider the possibility of realities we can't even begin to comprehend. Yet, it also raises important questions about the nature of science itself. How do we study something that, by definition, lies beyond our reach? And if we can't test the multiverse theory, does it belong in the realm of science at all? These questions make the multiverse one of the most divisive topics in cosmology. Some see it as a bold and necessary step forward, while others view it as a step too far into the unknown. But whether the multiverse is real or not, it serves as a powerful reminder of how much we still have to learn about the cosmos. As we continue to explore the mysteries of the early universe, the multiverse theory invites us to dream bigger and question deeper, pushing the boundaries of what we thought was possible. Next, we'll dive into another fascinating mystery: how quantum mechanics might hold the key to understanding the very origins of the universe. Now, let's take a step into the microscopic world of quantum mechanics, where the rules of reality seem to bend and twist in ways that defy our everyday understanding. Could the origins of the universe itself be rooted in these strange, subatomic phenomena? This is the mystery of the quantum origins of the universe, a topic that bridges the gap between the smallest particles and the vast cosmos. At the heart of this mystery lies the concept of quantum fluctuations. In the quantum realm, particles pop in and out of existence in a chaotic dance driven by the uncertainty principle. These tiny, random fluctuations might seem insignificant, but some scientists believe they could have played a crucial role in the birth of the universe. Imagine the early universe as a seething sea of energy where quantum fluctuations created tiny ripples. Over time, these ripples could have grown, seeding the large-scale structures we see today: galaxies, clusters, and the cosmic web itself. One of the most compelling theories linking quantum mechanics to the universe's origins is the idea of quantum tunneling. This phenomenon allows particles to tunnel through barriers that would be impossible to cross under classical physics. Some researchers suggest that the universe itself could have emerged from a quantum tunneling event, transitioning from a state of nothingness into the expanding cosmos we know today. It's a radical idea, but one that highlights the profound connection between the quantum world and the universe at large. Another key piece of the puzzle is inflation, the rapid expansion of the universe just after the Big Bang. Quantum fluctuations during this period could have left an imprint on the cosmic microwave background, the faint afterglow of the Big Bang. These imprints, known as anisotropies, provide a snapshot of the early universe and offer clues about how quantum mechanics shaped its evolution. In this way, the quantum world might hold the key to understanding not just the universe's birth, but its entire structure. But how do we reconcile the bizarre, probabilistic nature of quantum mechanics with the deterministic laws that govern the cosmos on larger scales? This is one of the biggest challenges in modern physics. Some theories, like quantum gravity, aim to bridge this gap, proposing that the fabric of spacetime itself is woven from quantum particles. If true, this would mean that the universe's origins are deeply intertwined with the quantum realm, blurring the line between the very small and the unimaginably large. The quantum origins of the universe remain one of the most tantalizing mysteries in cosmology. They challenge us to rethink our understanding of reality, from the tiniest particles to the vast expanse of the cosmos. While many questions remain unanswered, the exploration of quantum mechanics offers a glimpse into the fundamental forces that shape the universe, and perhaps even the forces that continue to shape its destiny. Next, we'll explore another elusive player in the cosmic drama: neutrinos and their mysterious role in the early universe. Now, let's turn our attention to one of the most elusive and enigmatic particles in the cosmos: neutrinos. These ghostly particles, often called the ghosts of the universe, are so tiny and nearly massless that they can pass through entire planets without interacting with anything. Yet, despite their elusive nature, neutrinos play a crucial role in shaping the early universe and remain one of the most fascinating mysteries in cosmology. Neutrinos are produced in vast quantities during high-energy events, such as nuclear reactions in stars, supernova explosions, and even the Big Bang itself. In fact, the early universe was teeming with neutrinos, and they continue to permeate space today, zipping through everything including you at nearly the speed of light. But here's the catch: neutrinos interact so weakly with matter that detecting them is incredibly challenging. This makes studying them a monumental task, yet their importance to our understanding of the cosmos cannot be overstated. One of the key mysteries surrounding neutrinos is their mass. For decades, scientists believed neutrinos were completely massless, but experiments revealed that they do have a tiny amount of mass, though exactly how much remains unknown. This discovery was groundbreaking because it challenged the standard model of particle physics, which had long assumed neutrinos were massless. The fact that neutrinos have mass means they could have influenced the formation of large-scale structures in the universe, such as galaxies and galaxy clusters, by subtly affecting the distribution of matter in the early cosmos. Another intriguing aspect of neutrinos is their ability to change flavors. Neutrinos come in three types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. As they travel through space, they can oscillate or switch between these flavors. This phenomenon, known as neutrino oscillation, was a major discovery that not only confirmed neutrinos have mass, but also opened up new questions about their behavior and role in the universe. For instance, could neutrino oscillations have played a part in the matter-antimatter asymmetry we see today? This is one of the many puzzles scientists are still trying to solve. Neutrinos also hold clues to some of the most violent events in the universe, such as supernova. When a massive star explodes, it releases an enormous burst of neutrinos, carrying away most of the star's energy. These neutrinos can provide a unique window into the inner workings of supernova, helping us understand how these explosions shape the cosmos and contribute to the creation of heavy elements like gold and uranium. In fact, detecting neutrinos from a supernova could give us real-time insights into the collapse of a star, something that's nearly impossible to observe directly. But perhaps the most profound mystery surrounding neutrinos is their connection to the very early universe. During the first few seconds after the Big Bang, neutrinos were among the most abundant particles in existence. They were so numerous that they formed a neutrino background, similar to the cosmic microwave background, which is the afterglow of the Big Bang. If we could detect this neutrino background, it would provide an unprecedented glimpse into the universe's infancy, revealing details about its temperature, density, and expansion that are currently hidden from us. Despite their ghostly nature, neutrinos are key players in the cosmic story. They challenge our understanding of particle physics, influence the formation of the universe's largest structures, and hold secrets about the most energetic events in the cosmos. Yet, their elusive behavior means there's still so much we don't know. As scientists continue to develop more sensitive detectors and innovative experiments, the hope is that neutrinos will reveal even more about the universe's origins and evolution. Next, we'll dive into another cosmic mystery, the formation of heavy elements, and how events like supernova and neutron star collisions forged the building blocks of the universe as we know it. Now, let's shift our gaze to one of the most awe-inspiring processes in the cosmos, the formation of heavy elements. While the early universe was dominated by the simplest elements, hydrogen and helium, it's the heavier elements like gold, uranium, and iron that make up the building blocks of planets, life, and even the device you're using to watch this video. But how did these heavy elements come to be? The answer lies in some of the most violent and energetic events in the universe, supernova and neutron star collisions. When the universe was young, it was a much simpler place. The Big Bang produced vast amounts of hydrogen and helium, but heavier elements like carbon, oxygen, and gold didn't exist yet. These elements had to be forged in the hearts of stars through a process called nucleosynthesis. In the cores of stars, extreme temperatures and pressures cause hydrogen atoms to fuse into helium, and over time, this fusion process creates heavier elements like carbon and oxygen. But even the most massive stars can only produce elements up to iron through fusion. So, where do the truly heavy elements come from? That's where supernova come in. When a massive star exhausts its fuel, it can no longer support itself against the crushing force of gravity. The core collapses, triggering a cataclysmic explosion known as a supernova. This explosion is so powerful that it can outshine an entire galaxy for a brief moment. But more importantly, the intense energy and pressure during a supernova create the perfect conditions for the formation of elements heavier than iron, such as gold, silver, and uranium. These elements are then scattered into space, enriching the surrounding gas and dust clouds, which eventually form new stars, planets, and even life. But supernova aren't the only cosmic forges. Neutron star collisions, or kilonovae, are another crucial source of heavy elements. Neutron stars are the incredibly dense remnants of supernova, packing the mass of a star into a sphere just a few miles across. When two neutron stars collide, the resulting explosion is so energetic that it produces a flood of heavy elements. In fact, a single neutron star collision can create enough gold to outweigh the entire Earth. These collisions are rare, but they're thought to be responsible for a significant portion of the heavy elements in the universe. The discovery of neutron star collisions as a source of heavy elements was a major breakthrough in astrophysics. In 2017, scientists observed the collision of two neutron stars for the first time, using both gravitational waves and light. This event, known as GW170817, confirmed that neutron-star collisions are indeed a key source of heavy elements like gold and platinum. It also provided a glimpse into the incredible processes that shape the universe on the largest scales. The formation of heavy elements is a story of cosmic alchemy, where the most violent events in the universe create the very materials that make life possible. Without supernova and neutron-star collisions, the universe would be a much simpler and far less interesting place. These processes not only enrich the cosmos with heavy elements, but also set the stage for the formation of planets, the emergence of life, and the evolution of galaxies. As we continue to explore the mysteries of the early universe, the next enigma we'll uncover is the strange alignment of cosmic microwave background features known as the axis of evil, and what it could mean for our understanding of the cosmos. Now, let's turn our attention to one of the most puzzling anomalies in the cosmos, the axis of evil. This mysterious alignment in the cosmic microwave background, or CMB, has left scientists scratching their heads and questioning some of the fundamental assumptions of our understanding of the universe. The CMB is the afterglow of the Big Bang, a faint radiation that fills the entire universe and provides a snapshot of the cosmos when it was just 380,000 years old. It's one of the most important tools we have for studying the early universe, but it also holds some unexpected surprises, like the axis of evil. The axis of evil refers to a strange alignment of temperature fluctuations in the CMB. These fluctuations are tiny variations in the temperature of the radiation, and they're thought to be the seeds of all the large-scale structures we see in the universe today, like galaxies and galaxy clusters. According to the standard model of cosmology, these fluctuations should be randomly distributed with no preferred direction or alignment, but that's not what we see. Instead, the fluctuations appear to be aligned along a particular axis, almost as if the universe has a preferred direction. This alignment has been dubbed the axis of evil because it challenges some of the core principles of modern cosmology. So, what could be causing this mysterious alignment? One possibility is that it's simply a statistical fluke, a random pattern that just happens to look significant. But the odds of such a fluke occurring are incredibly low, which has led some scientists to propose more exotic explanations. For example, the alignment could be evidence of something beyond our current understanding of physics, like a pre-Big Bang structure or a multiverse. It might even suggest that our universe is not as isotropic or uniform in all directions, as we've always assumed. If that's the case, it could force us to rethink some of the most basic assumptions about the cosmos. The implications of the axis of evil are profound. If it's not just a fluke, it could mean that our understanding of the universe is incomplete. The standard model of cosmology, which has been incredibly successful at explaining a wide range of observations, might need to be revised or even replaced. This would be a major shift in our understanding of the cosmos, with implications for everything from the nature of dark energy to the ultimate fate of the universe. It's a reminder that, even with all the progress we've made, there's still so much we don't know. As we continue to probe the mysteries of the early universe, the axis of evil stands as a tantalizing clue that there's more to the cosmos than meets the eye. Whether it's a statistical anomaly or a sign of something deeper, it challenges us to keep questioning, exploring, and pushing the boundaries of our knowledge. And with that, we move on to another cosmic mystery, the elusive magnetic monopoles, and why they've never been observed despite being predicted by some of our most fundamental theories. Now, shifting our focus to another intriguing puzzle, let's explore the mystery of the missing magnetic monopoles. These hypothetical particles, predicted by grand unified theories, are supposed to be the magnetic equivalent of electric charges, single poles of magnetism, either north or south, existing independently. Yet, despite decades of searching, scientists have never observed a single magnetic monopole. So, where are they, and why do they remain so elusive? grand unified theories which aim to merge the fundamental forces of nature into a single framework, suggest that magnetic monopoles should have been abundant in the early universe. These theories propose that as the universe cooled after the Big Bang, phase transitions occurred, creating defects in the fabric of spacetime. These defects could have given rise to magnetic monopoles, much like cracks forming in ice as water freezes. If this is true, we should expect to find at least some remnants of these particles today, but so far, nothing. One possible explanation for their absence is inflation, the rapid expansion of the universe just after the Big Bang. If inflation occurred, it could have diluted the density of monopoles to such an extent that they became incredibly rare, making them nearly impossible to detect. Another idea is that monopoles might have decayed or transformed into other particles over time, leaving no trace for us to find. Alternatively, they could be hiding in regions of the universe we haven't yet explored, or perhaps they interact with matter in ways we don't yet understand. The search for magnetic monopoles isn't just an academic exercise. If they exist, they could provide crucial insights into the nature of the early universe and the unification of forces. They might also help explain why the universe is dominated by matter rather than antimatter, as some theories suggest monopoles could have played a role in this imbalance. Discovering them would be a monumental breakthrough, potentially reshaping our understanding of physics and cosmology. Despite their elusiveness, scientists haven't given up the hunt. Experiments using advanced detectors, such as those in particle accelerators and deep underground labs, continue to search for even the faintest signs of these mysterious particles. While the results so far have been inconclusive, the quest for magnetic monopoles remains a fascinating chapter in our exploration of the cosmos. As we ponder the mystery of the missing monopoles, we're reminded once again of how much we still have to learn about the universe. Their absence challenges us to refine our theories, develop new detection methods, and keep pushing the boundaries of science. And with that, we turn our attention to another cosmic enigma: the formation of magnetic fields in the early universe and how they shaped the cosmos we see today. Now, as we venture into another fascinating corner of the cosmos, let's unravel the mystery of the early universe's magnetic fields. These invisible forces, which we often take for granted in our daily lives, play a crucial role in shaping the universe on a grand scale. But how did they form in the first place, and what influence did they have on the birth and evolution of galaxies? These questions lie at the heart of one of the most intriguing puzzles in cosmology. Magnetic fields are everywhere, from the magnets on your fridge to the vast magnetic fields that permeate galaxies. But their origins in the early universe remain shrouded in mystery. Scientists believe that these fields likely emerged during the universe's infancy, possibly within the first few moments after the Big Bang. One leading theory suggests that tiny fluctuations in the primordial plasma, a hot, dense soup of particles, could have generated weak magnetic fields. Over time, as the universe expanded and structures like galaxies began to form, these fields may have been amplified, shaping the cosmic landscape we see today. But here's the catch: detecting these ancient magnetic fields is incredibly challenging. Unlike stars or galaxies, magnetic fields don't emit light, making them invisible to traditional telescopes. Instead, researchers rely on indirect methods, such as observing the effects of magnetic fields on cosmic rays or the polarization of light from distant objects. These observations provide clues, but piecing together the full picture requires a combination of advanced technology and theoretical models. The role of magnetic fields in galaxy formation is another layer of this mystery. These fields are thought to influence how gas collapses to form stars and how galaxies evolve over billions of years. For instance, magnetic fields can regulate the flow of gas within galaxies, preventing it from collapsing too quickly and controlling the rate of star formation. They may also play a part in shaping the spiral arms of galaxies or even powering the jets of material ejected by supermassive black holes. Yet, despite their importance, we still don't fully understand how these fields interact with other cosmic processes. One of the biggest challenges in studying early magnetic fields is their faintness. By the time their influence reaches us billions of years later, the signals are incredibly weak. Additionally, the universe's expansion has stretched and diluted these fields, making them even harder to detect. To overcome these obstacles, scientists are developing new tools and techniques, such as more sensitive radio telescopes and sophisticated simulations to peer deeper into the cosmic past. As we continue to explore this mystery, we're reminded of how interconnected the universe truly is. Magnetic fields, though invisible, are woven into the fabric of the cosmos, influencing everything from the smallest particles to the largest structures. Understanding their origins and evolution could unlock new insights into the universe's history and the forces that shaped it. With this in mind, we now turn our attention to another profound question: the nature of time itself. How did time emerge in the early universe, and what role does it play in the grand cosmic story? Stay with us as we dive into this timeless mystery next. Now, let's shift our gaze to one of the most fundamental yet elusive mysteries of the cosmos: the nature of time itself. What exactly is time, and how did it emerge in the early universe? These questions might sound philosophical, but they lie at the heart of our understanding of the universe's origins and evolution. Time, as we experience it, flows in one direction, from past to future. This one-way flow is often referred to as the arrow of time. But why does time have this direction, and was it always this way? To explore this, we need to go back to the very beginning, to the moments just after the Big Bang. In the early universe, time as we know it may not have existed in the same way. Some theories suggest that time itself could have emerged alongside space and matter as part of the fabric of the universe. But how? One key idea comes from the second law of thermodynamics, which states that entropy or disorder always increases over time. This increase in entropy gives us the arrow of time, explaining why we remember the past but not the future. In the early universe, entropy was incredibly low, and as the universe expanded and evolved, entropy increased, creating the flow of time we experience today. But this raises another question: why was the early universe in such a low entropy state to begin with? This is still one of the biggest puzzles in cosmology. Another fascinating theory involves the concept of quantum gravity, which attempts to unify the laws of quantum mechanics with gravity. In this framework, time might not be a continuous flow, but rather something that emerges from more fundamental processes. Some physicists even suggest that time could be an illusion, a byproduct of our perception rather than a fundamental feature of the universe. If true, this would radically change our understanding of reality. The role of time in the early universe is also tied to the formation of structures like galaxies and stars. Without the passage of time, the universe would remain a featureless soup of particles. Time allows for change, for the growth of complexity, and for the emergence of the cosmos as we know it. But what if time behaves differently on cosmic scales? Could there have been moments in the early universe when time flowed backward or stood still? These are questions that challenge our very understanding of existence. As we ponder the nature of time, we're reminded of how deeply interconnected it is with the universe's story. Time isn't just a backdrop, it's an active participant, shaping the cosmos and our place within it. And while we've made incredible strides in understanding its role, many mysteries remain. What caused time to begin? Does it have an end? And could there be universes where time operates entirely differently? With these questions in mind, we now turn to another profound mystery: the information paradox. What happens to information swallowed by black holes, and what does this tell us about the early universe? Stay with us as we explore this mind-bending puzzle next. Now, let's venture into one of the most perplexing puzzles in modern physics, the information paradox. This mystery revolves around a seemingly simple question: what happens to information that falls into a black hole? At first glance, it might not sound like a cosmic conundrum, but it strikes at the very heart of our understanding of the universe and its fundamental laws. Black holes, as we know, are regions of space-time where gravity is so intense that nothing, not even light, can escape. According to Einstein's theory of general relativity, anything that crosses a black hole's event horizon is lost forever, crushed into the singularity at its core. But here's the catch: quantum mechanics, the framework that governs the behavior of particles at the smallest scales, tells us that information cannot be destroyed. It must be preserved even if it's scrambled or transformed. So, what happens to the information swallowed by a black hole? Does it vanish, or is it somehow retained? This contradiction between general relativity and quantum mechanics is the essence of the information paradox. It's a clash between two of the most successful theories in physics, and resolving it could unlock profound insights into the nature of reality. One of the leading ideas to address this paradox comes from Stephen Hawking, who proposed that black holes aren't entirely black. They emit radiation, now known as Hawking radiation, which causes them to slowly evaporate over time. But here's the twist: if a black hole evaporates completely, what happens to all the information it consumed? Does it disappear, or is it somehow encoded in the radiation? Some physicists suggest that the information is preserved, perhaps hidden in the intricate details of Hawking radiation, or stored in the black hole's event horizon. Others propose more radical ideas, like the holographic principle, which suggests that all the information about what falls into a black hole is encoded on its surface like a cosmic hologram. This would mean that the three-dimensional reality we perceive is actually a projection of information stored on a two-dimensional boundary. If true, it would revolutionize our understanding of space-time itself. The implications of the information paradox extend far beyond black holes. It touches on the very fabric of the early universe. If information can be lost or destroyed, it challenges our understanding of how the universe evolved from its initial state. The Big Bang, after all, was a moment of extreme density and energy, not unlike the conditions inside a black hole. If information isn't preserved, how can we trace the universe's history back to its origins? On the other hand, if information is always conserved, it could provide a way to reconstruct the universe's past, offering clues about its earliest moments. This paradox also raises questions about the nature of time and causality. If information can be scrambled or lost, does that mean the past is fundamentally unknowable? Or is there a deeper layer of reality where all information is preserved, waiting to be decoded? These questions push the boundaries of our knowledge, forcing us to rethink the very foundations of physics. As we grapple with the information paradox, we're reminded of how much we still have to learn about the universe. It's a mystery that bridges the microscopic world of quantum particles and the vast expanse of black holes, connecting the early universe to the cosmos we see today. And while we don't yet have all the answers, the journey to solve this paradox is leading us to new and exciting frontiers in science. With this in mind, let's turn our attention to another groundbreaking idea, the holographic principle. Could the universe itself be a hologram, and what would that mean for our understanding of reality? Stay tuned as we explore this mind-bending concept next. Now let's dive into one of the most mind-bending ideas in modern physics, the holographic principle. This theory suggests that our three-dimensional universe might actually be a projection of information stored on a two-dimensional surface like a cosmic hologram. At first, this might sound like science fiction, but it's a serious proposal that could reshape our understanding of reality itself. The holographic principle emerged from attempts to solve the information paradox we just explored. If information isn't lost in black holes, where does it go? some physicists like Leonard Susskind and Gerard T. Hooft proposed that all the information about what falls into a black hole is encoded on its event horizon, the boundary that marks the point of no return. This idea led to a broader hypothesis. What if the entire universe works this way? What if everything we see, from galaxies to stars to planets, is just a projection of information stored on some distant two-dimensional surface? This principle challenges our everyday experience of space and time. We perceive the universe as three-dimensional with length, width, and depth, but the holographic principle suggests that this might be an illusion. Instead, the true reality could be a flat, two-dimensional surface where all the information about the universe is stored. Our three-dimensional world would then be like a hologram, a kind of cosmic projection of that underlying information. So, how does this connect to the early universe? During the Big Bang, the universe was incredibly small and dense, with all its energy and information packed into a tiny volume. If the holographic principle is correct, this early state might have been encoded on a two-dimensional surface, and as the universe expanded, that information was projected into the three-dimensional space we see today. This could provide a new way to understand the origins of the universe and how it evolved from its initial conditions. But why is this theory so radical? For one, it turns our intuitive understanding of reality on its head. We're used to thinking of space and time as fundamental, but the holographic principle suggests they might be emergent properties arising from something more basic. It also implies that the universe has a kind of pixelation, a limit to how much information can exist in any given region of space. This idea has profound implications for physics, potentially bridging the gap between quantum mechanics and general relativity. The holographic principle isn't just a theoretical curiosity, it has practical implications too. For example, it could help us understand the behavior of black holes and the nature of space-time itself. It might even provide clues about the ultimate fate of the universe. But as fascinating as this idea is, it's still a hypothesis. Scientists are working to find evidence that could confirm or refute it, using tools like gravitational wave detectors and experiments in quantum gravity. As we ponder the holographic principle, we're reminded of how much we still have to learn about the cosmos. It's a theory that challenges our deepest assumptions about reality, pushing us to think in entirely new ways. And while it might seem strange, it's a testament to the power of human imagination and curiosity, driving us to explore the most profound mysteries of the universe. With this in mind, let's turn to the final and perhaps most profound question of all. Why does the universe exist in the first place? Stay with us as we explore the ultimate mystery of existence itself. Now, as we reach the final and most profound mystery of all, we're faced with a question that has puzzled humanity for centuries. Why is there something instead of nothing? This isn't just a question for scientists or philosophers, it's one that touches the very core of our existence. Why does the universe exist at all? Why is there a cosmos filled with galaxies, stars, planets, and life, rather than an endless void of nothingness? From a philosophical perspective, this question has been debated for millennia. Thinkers like Aristotle, Leibniz, and Heidegger have all grappled with it, each offering their own interpretations. Leibniz, for example, argued that there must be a sufficient reason for the existence of the universe, pointing to the idea of a necessary being, often interpreted as God as the ultimate cause. On the other hand, existentialist philosophers like Jean-Paul Sartre suggested that existence precedes essence, meaning the universe simply is, without needing a reason or purpose. But what does science have to say about this? While science doesn't deal with questions of purpose or meaning in the same way philosophy does, it does offer some fascinating insights. The Big Bang theory tells us that the universe began around 13.8 billion years ago, expanding from an incredibly hot and dense state. But it doesn't explain why the Big Bang happened in the first place. Some scientists propose that the universe could have emerged from a quantum fluctuation, a random event in the fabric of space-time that allowed something to come from nothing. Others suggest the possibility of a multiverse, where our universe is just one of countless others, each with its own set of physical laws. Then there's the concept of the zero-energy universe, which suggests that the total energy of the universe might actually be zero. If this is true, it could mean that the universe is essentially a fluctuation in a sea of nothingness, balancing positive energy with negative gravitational energy. In this view, the universe might not need an external cause. It could simply be a self-contained system that arose naturally from the laws of physics. But even with these theories, the question remains, why do these laws of physics exist at all? Why is there a framework that allows for the existence of something rather than nothing? Some scientists and philosophers argue that this question might be beyond the scope of human understanding. After all, our brains evolved to solve practical problems, not to comprehend the ultimate nature of reality. Yet the pursuit of this question drives us forward. It's what fuels our curiosity, our desire to explore, and our quest for knowledge. Whether through philosophy, science, or even art, humanity continues to grapple with this profound mystery, seeking answers that might one day bring us closer to understanding the true nature of existence. As we wrap up our journey through the mysteries of the early universe, we're left with a sense of awe and wonder. The cosmos is filled with questions that challenge our understanding and push the boundaries of what we know. And while we may not have all the answers, the pursuit of these mysteries reminds us of the beauty and complexity of the universe we call home. Thanks for joining us on this incredible exploration. Don't forget to like, subscribe, and hit the notification bell to stay tuned for more cosmic adventures. And so, as we bring this cosmic journey to a close, let's take a moment to reflect on the incredible mysteries we've explored together. From the enigmatic Big Bang Singularity to the elusive nature of dark matter and dark energy, from the puzzling horizon problem to the profound question of why there's something instead of nothing, each mystery has revealed just how much we still have to learn about the universe. These questions aren't just scientific curiosities, they're windows into the very fabric of reality, challenging us to rethink what we know and inspiring us to push the boundaries of human understanding. What makes these mysteries so captivating is that they're not just problems to be solved, they're invitations to explore. They remind us that the universe is far more complex, more beautiful, and more mysterious than we could ever imagine. And while we've made incredible strides in unraveling some of these cosmic puzzles, many remain unsolved, waiting for the next generation of thinkers, dreamers, and explorers to uncover their secrets. But here's the thing, the pursuit of these mysteries isn't just for scientists or experts. It's for all of us. Every time we look up at the night sky, every time we wonder about the origins of the cosmos, we're participating in this grand quest for knowledge. And that's what makes it so exciting. We're all part of this journey together. So, what do you think? Which of these mysteries fascinates you the most? Do you have your own theories or questions about the early universe? Let us know in the comments below. We'd love to hear your thoughts and keep the conversation going. And if you've enjoyed this exploration of the cosmos, don't forget to hit that like button, subscribe to the channel, and ring the notification bell so you never miss out on our next adventure into the wonders of the universe. Thank you for joining us on this incredible journey through the mysteries of the early universe. The cosmos is vast and its secrets are endless, but one thing's for sure, the more we discover, the more we realize just how much there is to explore. Until next time, keep looking up, keep wondering, and keep exploring. The universe is waiting.